So some of you in the group, some of you or some of the others in the group were complaining that the speed is too much. Right? Saying it's too much work, right? Anybody here? Don't be afraid. Can you raise your hand if you believe that it's too fast or thing. Anybody who believes the way you are pushing forward is too fast, let us know. None of you think it's too fast, huh? You think it's too fast?
Too fast.
Too fast?
It's okay for the speed, but there's a lot of assignments. Yeah. Like we don't know, we need to.
Can you speak louder, please?
We don't know, we need to recap what we took because I am a graduate from 2 years. So now I need to recap everything from maybe 2020.
Exactly. That's the whole purpose is for recapping.
Yeah, so I don't know if I should focus on my lessons or I should solve the assignment or should I prepare to the exam. So I think the assignment.
There is no way to prepare for exam before you review the course and do the homework, right?
Yeah, so I think.
If you review the course and homework, you are prepared for exam.
I think the assignments need to be questions for the students if they want to exercise for the exam.
It's the same thing.
Yeah, but
it's about knowing the game. When you start knowing it, then you are prepared for exam.
Because there's 3 assignments in 1 week, so that's.
It actually should be 5 assignments in 1 week. Last week there was only 3. It's going to be 5 assignments. It's going to be assignments for every day. Huh? Yeah, what I understand. So, but what we can do, because remember, I kept repeating the philosophy. The purpose is to maximize your learning and foundation. So if the speed is too much, for some people may want to do faster, some people may want to do slower. If the speed is too much, what we can do is we can probably replicate the same class.
It's not about the speed, but it's about the assignment has too many questions. So if we, in my suggestion, if we did one assignment, but it has multiple questions, like for the whole week, I think it's much better. It's be one assignment and it has questions.
The worry is how can you sit in the exam and solve all those problems in that limited time if you are.
The rest of the questions can be an exercise for us, but
it's exercise.
But as an assignment, if there is a deadline, I think one question from each topic.
No. So what we can do is we can say, okay, you can solve your homeworks before the exam anytime you want. That's true. The fact that they are offering to see your solutions and giving you advice on that is to help you better understand your weaknesses in the problem. Right? So the high level question is whether we had 4 sessions last week, right? Yeah. 4 or 5, right? But 5 sessions last week, and we will be having basically 3 sessions this week before the exam. 8 sessions. Yeah, total is planned 8 sessions, right?
It was planned, but
yeah. So now you are behind. So the first question is like 8 to 10 sessions for remembering circuit theory. Can be enough for some people, can be too tight for some people. So it depends on how much you remember or how much you have studied before. Some of you haven't studied it before, so it's the first time you're going. If it's the first time, definitely it's on the fast track. If you have studied it and you're remembering it, it's okay if you have studied it well. If you haven't studied it well, it's pretty much like restudying it again, then it may be a little fast. So our purpose is just to make sure that whatever you learn with high quality. Yes, we were planning to pack certain amount of material in the 2 months to maximize your outcome. But if that sacrifices the quality of the learning, we can adjust the speed for some. But we also understand that the backgrounds are different. Different people may have different level of interest or time to attend. I was thinking, reading your messages to Dr. Hassan, that maybe what we can do is we can actually create a slower track as well for those who want to go more slowly learn at a slower pace so that they don't fall behind on the topic. And then basically, of course, the ones who go slower, in 2 months, they will cover less material. My idea was that in 2 months, we finish 5 general areas: circuits, then basics of devices, electronic circuits, signal systems, control, feedback, and electromagnetics. Now, if we slow down in 2 months, we will not be able to cover all of that. But the other way is to basically give the option. The ones who want to go fast, we go. The ones who want to slow down, maybe we cover 3 topics. And then we can repeat the rest of the things for them later on, online or whichever way, if they want to read. But the whole purpose is just making sure that your foundation becomes solid. And then later, when we go to the follow-on courses, of course, again, it's important to start on a solid foundation, but then if people don't have time to follow all of it, maybe, for example, for those who go more slowly, we finish the foundation instead of 2 months, we finish it in like 3 months, 4 months. So they may be missing the first, but maybe the digital course, and then they will start with the analog course or whatever later on. So that we adjust the pace for everyone. That was my thinking. Now, let's say if I give you 2 options, the current speed and the slow speed, which one do you think? You go reduce speed. You go reduce speed. I want to understand what works best. Because at the end, all we care is how much you have left.
We need to balance the assignments and the amount of materials that we use. Because if we have a lot of assignments in just 1 week, most of us will just rely on ChatGPT to solve them, and I won't.
But if you use ChatGPT, you don't learn.
Yeah, exactly. So 1 to 2 assignments in a week is perfect.
It is not like how many topics we need for the assignment.
A suggestion. You just don't do assign. If you're okay with this, instead of giving these homeworks as assignments, we say these are the things you have to know and you have to practice by yourself. If you have questions, come and ask.
Much better.
But if you fail in the exam because you haven't been able to solve the problem by yourself, because in the exam you don't have that GPT, we just give you feedback. You say, okay, first round you failed. We are happy to say, okay, go study again and come back and do another exam 2 weeks later. You can keep taking exams until your foundation is, but we will not pass you unless you are able to solve the problems. Right? Because the exam is only a measure for yourself on whether you are comfortable enough with the material. Right? There is no failure. It's only success. But the success may require more time. Does it make sense? Will it make it attractive? Okay, so moving forward, anything that you call assignment. I think we still should keep the option of assignment. So we just say review problems, and then some of them we will announce as assignment. Does it make sense? So some of them.
You are happy with that?
No, so some of the homeworks you announce it as assignment. Then they have to. So, because we also owe you to give you feedback that you are progressing and you're doing the work. We can make it very easy. We can say, okay, you don't need to come to the class. You can go review by yourself. It's self-learning at the end. That's okay. The class is here to help. The assignments are here to help. And the exam is there to help you measure it. We just try to remind you what are the topics that you need to know. We cannot make you know it. You have to learn it by yourself. You can explain, you can help, but at the end it's your. Any opinion? What should we do? Yes. No.
All good.
The
I think it's a good idea for the science. Like when we do it, make it like more as a practice exercises.
you are free to choose whichever you want. If you solve it, you need to discuss with us to better understand it or things, feel free to contact us. You don't need to deliver. The only thing you need to deliver is to sit at the exam and solve. Simple.
That's better.
It's better. It's okay. Yes. Can you speak louder, please?
Can you provide a model solution for the assignment?
The solutions.
Sure. I have too many solutions for you because almost not half, but maybe 1/3 of the students ChatGPT and all for it.
ChatGPT does it correctly.
Yes, most of them.
Okay, so there is good news. You know what is good news?
I will send
What is the good news?
solution.
The final answer is just,
Yeah.
not the first.
The good news is that companies like us can hire ChatGPT instead of hiring you guys. And we spend $10 a month instead of paying salaries. That's the good news. The bad news is, as humans, we are losing to ChatGPT. So how should we win? Should be able to win. And how you can win is by not just but if it's about memorizing or repeating the same instructions and things, ChatGPT will do it better than all of us. The part that we should win at is on the humane side of it, which means understanding it, coordinating it, connecting it across disciplines, coordinating with people, getting things done. ChatGPT cannot do. But then you have to understand it at least to a level that you can beat ChatGPT in certain angles. If ChatGPT beats us in every angle, we can put ChatGPT to teach ChatGPT, and all of us are out of job. Right? Now, of course, you can use creatively, you can use ChatGPT in any possible way that you think that you can creatively use it to become a more powerful engineer. That's why I'm not against using ChatGPT. I actually encourage you. Use it. But when you use it, try to understand. Are you the one using ChatGPT or driving it, or is ChatGPT using it? ChatGPT also learns every time that we give these problems. ChatGPT learns. ChatGPT can do your work. You can also teach ChatGPT. But at the end, you have to know how to drive it well so that you become more efficient. You don't want to lose to ChatGPT. Make sense? But definitely, you can use ChatGPT to become more efficient, reviewing or understanding. And then the other thing is, this wasn't available when we were studying. Any of these topics, you can go on YouTube, watch videos of it. You can put it on double speed, quickly grasp it up. Then you can ask ChatGPT to re-summarize it. You can ask ChatGPT that I didn't understand this, can you explain? But then at the end, we do the exam just to make sure that at least those levels that we know you have achieved. Why? Because that's a basic that would allow you to use ChatGPT properly. Of course, actually for us, we use simulators. Simulators solve all those complex problems much better than ChatGPT. But to use it properly, you have to understand what you're doing. Right? So we don't need to go slower track, we can continue on the same speed. Let's see. Okay, we'll do the first exam and then we'll see how it works. If we see that, oh no, the performance is really bad, then we say, okay, you know what? You didn't study well enough for the first exam. While we move to the second topic, say, okay, go also re-study the circuits. We'll do another exam 2 weeks later. Until you are actually learning all of it. Does it make sense? You're okay? Any better suggestion? Just don't want to be rigid saying no to the things that can help. Okay. Let's proceed.
That's part of the assignment. Since most of you told the assignment and sent the answer, I want one volunteer to solve it for us. But I think more than 40 people sent the answer. I want to check how confident you are.
One of our good ChatGPT users, we invite you to come here, repeat what ChatGPT did.
Yeah, I think we can explain what that.
The kinds of-
All, yeah, all the
Yes.
Is it true? Is it correct? Deep path of Mexico. That means the way these paths come from here to here, these paths are they the same? That can easily divide the current by 3. Yeah, but you are using symmetry. How did you find that all currents should be equal?
Because it is the right of treatment.
All is equal, but you know, the last assignment, the last step, it was here. From here to here, all these passes are here. The path in similar to each other. But for this case, if you come from this path to this node, or if you come from this path to this node, they are totally different. That means you cannot easily say the current is equal in all branches.
Because it's not symmetric.
It is symmetric, but not. You should find a symmetrical plane. Anyone else? Thank you. You're with right, that we should find a symmetrical plane, but it's not all symmetric. Anyone else can help? You thought it, no? Okay. No, we are looking for. Which one?
So it's not the,
Yeah. No, no, they are not.
the same. What is this?
Can you write it?
So what is the,
Oh, one. They are the same. Up to you. One. 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 Right. That is symmetrical display. That's diagonal. Yeah. That means if I apply a voltage here, if I apply voltage, this voltage should be equal to this one, yeah, because they are symmetrical regarding to this plane. This voltage be equal to this one, yeah. Because this path and this path both are same. I'm looking from this node and this, yeah. If you consider a diagonal plane that crosses this node and this, let us say green plane. I'm showing. I draw. So in this plane, regarding to this plane, this point should be equal to this point. They are mirror. Okay. This node is mirror to this node. That means you can easily short them together because they are same, they have same potential. If we connect these two nodes together, what will happen? Absolutely. These two resistors are, what's the relationship between these two resistors? They are parallel. I can write one here. These two are parallel, I can write R over 2. These two parallel R over 2. This one and this one. Again, both terminals are connected together. They are parallel. This one and this one. Again, parallel. This one. And these two are again. Now you can find easily the equivalent resistor of how applying transformation analysis, or you can find two delta star but you have to compare the star model with the model. Since all extremes are equal, it should be multiplied by now these two are the with this one the result is 1.5 over again two series parallel. These two series parallel and the answer is how much? 3 over 3 over 2 over 3 over 1. That's it. Uh, about that, as we can only one.
You'll be able to visualize the entire process and even derive the energy stored in a capacitor. Let's jump right in. Understanding capacitors. Imagine a capacitor as a tiny Hello, students. Today, we're not just going to learn about capacitors. We're going to feel what happens inside them during charging and discharging. By the end of this video, you'll be able to visualize the entire process and even derive the energy stored in a capacitor. Let's jump right in. Understanding capacitors. Imagine a capacitor as a tiny supercharged battery. It has two metal plates separated by a small distance d. Keep in mind that capacitors are electrically neutral. This means that for every positive charge in the capacitor, there is an equal amount of negative charge as well. However, in our presentation here, we will only show the conventional direction of current. Let's imagine we connect a 9-volt battery to a capacitor. Here's what happens step by step. As soon as the connection is made, the battery starts hustling positive charges from one plate to the other. Each little charge, dq, needs some help from the battery to make the journey across. Initially, at the start, the capacitor's potential is 0 volts, while our battery is a solid 9 volt. The first few charges move easily, but as more charges pile up, the capacitor's plates start pushing back, saying, hey, we're full. The battery has to work harder to move more charges, building up potential energy in the capacitor. Second, you know that positive charges flow from the positive terminal to the negative terminal, which is the conventional direction of current. That is, the battery wants to make the charge flow clockwise. Now, one of the plates has an excess of positive charges, making it positively charged, while the other plate has an abundance of negative charges, making it negatively charged. These excess positive charges naturally want to flow back to balance the charges. If we think of the capacitor as a tiny battery, positive charges want to flow from positive to negative terminal of the capacitor, or we can say it wants to make the charge flow counterclockwise. But because the potential of the battery is higher, or rather the power to push the charges is higher, the battery will succeed in moving the charges clockwise until the voltage of the capacitor is comparable to that of the battery. An electric field forms between the plates, opposing further charge movement. This field grows stronger as more charge accumulates. Okay, now let's see the graphical representation of charge Q and time t. Graph for the process of charging. When you plot the charge Q on the capacitor against time t, you get a curve that looks like this. Initially, the charge increases quickly, but slows down as it approaches the maximum value. Understanding expression for the energy stored in the capacitor. So, when we insert a small charge, dq, into the plate of a capacitor, we have to do some work. We know that the work done per unit charge is equal to the potential energy, which we call V. Additionally, you know that the voltage across the capacitor is related to the charge Q on the capacitor and its capacitance C by the formula that says voltage equals charge Q divided by capacitance C. When we substitute Q by C into the equation for work done, we get work done equals Q by capacitance multiplied by dQ. We know that the total work done by the battery to insert charges into the capacitor is stored as the potential energy of the capacitor. To calculate the total work done, we need to integrate. We will integrate the small amount of work done, dW, and denote the resulting energy by U while integrating from zero charge to total charge Q. This will help us to find out how much work the battery had to do to insert all Q charges to fully charge the capacitor. First, we'll take the constant one by capacitance out of the integral. You know that the integration of Q dQ results in Q squared by 2. Then, substituting the upper and lower limits, we get 1 by 2 times Q squared by C. Here, we can write Q as capacitance C multiplied by voltage V. Simplifying this equation, we get 1 by 2 C V squared. Think of it like many positive charges being forcefully compressed in one place as if they are struggling to return to their neutral state. They want to come out, but the battery isn't letting them. But now, if we remove the battery, the charges will remain trapped in the capacitor, and we'll say the capacitor has become charged. The charges cannot flow because the circuit is still open. However, if we replace the battery with a bulb that has no internal EMF, the charges will flow back to their neutral state through the circuit. The capacitor will then function like a tiny battery, causing the bulb to glow for a while and then quickly discharge. This process is known as discharging of the capacitor. Now we can understand graphical representation of charge, Q, and time, T, graph, for the process of discharging. When you plot the charge, Q, on the capacitor against time, T, during discharging, the curve is the opposite of charging. It starts high and decreases rapidly at first, then slows down as it approaches 0. So that's all for this video. Thank you so much for watching.
See about that, well, I think for,
It's good.
I think only reporting.
Welcome to our 12th physics animation series. In previous videos, we explored how capacitors work and their capacitance equation, but in real circuits, a single capacitor isn't enough. Devices use capacitor combinations to store more charge or handle higher voltages. Let's understand how these combinations work and why they're so important. Imagine we have 3 capacitors, C1, C2, and C3, connected in series. But what does a series combination mean? It simply means that the capacitors are connected one after another in a single path, just like a chain. Now let's connect a battery to this series combination of capacitors. As soon as we do this, the battery pushes a certain amount of positive charge, Q, onto the first capacitor plate of C1. But here's where things get interesting. The positively charged plate of C1 repels the positive charge on the adjacent plate. This repelled charge moves away, leaving an equal amount of negative charge on that plate. Now, the positive charge moves forward to the next capacitor's plate and repeats the process. The positive plate repels the positive charge of the next plate, making it negative. The plate that loses positive charge becomes negative. This chain reaction continues across all capacitors in the series. Finally, when the last capacitor's plate sends its positive charge to the negative terminal of the battery, the circuit is complete. The same charge that the battery supplied from the positive end now reaches the negative end, maintaining a continuous flow of charge. This unique charge transfer mechanism ensures that all capacitors in a series combination have the same charge Q, which is a key property of series circuits. I got a lot of questions regarding that positive charge. Do not move. So here is the explanation from the perspective of electrons, not from the conventional current perspective, but from the movement of electrons, which are the real charge carriers. The battery's negative terminal pushes electrons onto the nearest plate of C3, making it negatively charged. These extra electrons repel electrons from the opposite plate of C3, leaving it positively charged. The repelled electrons move to C2's plate, making it negative, and push electrons away from its other plate, making that positive. This chain reaction continues. The electrons move to C1's plate, making it negative. The last plate of C1 loses electrons, becoming positive, and the freed electrons are pulled into the positive terminal of the battery. As a result, every capacitor has the same charge. Here's an important point to note. All capacitors in a series combination have the same charge, Q. While the charge, Q, is the same for all, the voltage is different based on their capacitance across each capacitor. We can express this as voltage across capacitor C1. V1 equals Q by C1. Voltage across capacitor C2. V2 equals Q by C2. Voltage across capacitor C3. V3 equals Q by C3. That's a series connection. The total voltage, V, is the sum of individual voltages. V equals V1 plus V2 plus V3. And here this V is the voltage or a potential difference of a battery. When we connect capacitors in series, we want to find a single equivalent capacitance, CE, that behaves the same as all the capacitors combined. To find this equivalent capacitance, we start with the definition of capacitance, which is CE equals Q by V, that is, charge stored per unit voltage. Now, in a series connection, the total voltage across the combination is this, which we have just calculated, and charge Q stored in each capacitor is same. Just after simplifying the equation, we will get 1 by CE equals 1 by C1 plus 1 by C2 plus 1 by C3, and so on to the n number of capacitors, 1 by Cn. This gives us the formula for equivalent capacitance at series combination. Now, let's understand what happens to the overall capacitance in a series connection. Does the total charge storing capacity increase or decrease? To visualize this, imagine we have 3 capacitors, each of the same capacitance C, connected in series. Using the formula, we get 1 by CE equals 3 by C, which gives CE equals C by 3. So we clearly see that the total equivalent capacitance decreases. Also, when all capacitors in the series have the same capacitance, we can use a simplified formula. If N is the number of capacitors and each has capacitance C, then CE equals C by N. For example, if we connect 10 capacitors, each of 5 microfarads in series, then CE equals 5 by 10, which gives 0.5 microfarad. So we clearly see that the total equivalent capacitance decreases. In fact, the equivalent capacitance in a series connection is always smaller than the smallest individual capacitor in the group. This is smaller than the capacitance of any single capacitor in the series. So, in summary, for series connection, 1, the charge Q remains the same on all capacitors. 2, voltage divides among the capacitors according to their capacitance. 3, the total capacitance always decreases. 4, equivalent capacitance is always smaller than the smallest capacitor in the series. In the next video, we will see how charge, voltage, and capacitance are distributed in parallel circuit. Thank you so much for watching. Hey there, welcome back. In our last video, we explored the combination of capacitors in series, right? Today, we're going to dive into the combination of capacitors in parallel. And let me tell you, this concept is super important because in most real-world applications, capacitors in parallel are often preferred over series combinations. Now, while series combinations can be helpful in certain situations, like voltage division or achieving specific voltage ratings, they tend to result in lower equivalent capacitance. So let's jump into it. And I promise it's going to be just as fascinating as last time. All right, let's visualize how a parallel combination of capacitors works. Imagine we have 3 capacitors labeled C1, C2, and C3. Now, in a parallel setup, these capacitors are connected side by side, all joined together at one point. Now, here's the key difference between parallel and series combinations. In parallel, when we connect these capacitors to a battery, the voltage across each of them is the same. There's no voltage drop between them. This is because all the capacitors share the same connecting points, like being on the same level in a way, no matter what. Can you believe this? That means the voltage across C1, C2, and C3 will be exactly the same as the battery's voltage. But hold on, how much charge will each capacitor hold? Well, that's where things get interesting. When the battery pushes charge into this parallel circuit, the charge doesn't distribute evenly between the capacitors. It's actually based on their capacity to store charge. As the positive charge accumulates on the first plate of each capacitor, the same amount of positive charge is pushed back into the battery from the second plate, like a beautiful balance of give and take happening inside the circuit. The charge each capacitor stores depends on its capacitance. Just imagine, one capacitor might hold a lot of charge easily, while another with lower capacitance will store less charge. So here's the thumb rule. In a parallel combination, the voltage is the same across all capacitors, but the charge stored in each capacitor will vary depending on their individual capacitances. Now, how do we calculate the charge stored in each capacitor? Well, it's actually quite simple. The charge on a capacitor is equal to its capacitance multiplied by the voltage across it. So for C1, charge is C1 times V. For C2, it's C2 times V. And for C3, it's C3 times V. Capacitors with higher capacitance will store more charge, while those with lower capacitance will store less. But how do we find the equivalent capacitance of this parallel combination? The equivalent capacitance is the total amount of charge divided by the total voltage. Since the voltage is the same across all capacitors, we just add up the charges stored in each one. So the total charge in the system is simply the sum of the individual charges. Q1 plus Q2 plus Q3. And since voltage is the same across each capacitor, it cancels out when we calculate the equivalent capacitance. What do we get? The equivalent capacitance, CD, is equal to C1 plus C2 plus C3, and so on, if you have more capacitors connected in parallel. This is huge. The equivalent capacitance is the sum of all the individual capacitances. So if we have 5 capacitors of the same capacitance, say C, the total capacitance will be 5C. In general, for N capacitors of the same capacitance, the equivalent capacitance will be NC. To wrap it up, let's quickly compare this to the series combination we studied in the last video. In a series combination, the voltage divides, but the charge stays the same across each capacitor. The equivalent capacitance is smaller than any of the individual capacitors. In a parallel combination, the voltage stays the same, but the charge divides between the capacitors based on their capacitance. The equivalent capacitance increases as you add more capacitors, making it larger than any individual capacitance in the circuit. So, in short, series, voltage divides, charge stays the same. Parallel, charge divides, voltage stays the same. And that's the beauty of how parallel capacitors work. More capacitance, more charge stored, and more flexibility for applications where you need that extra power. Isn't that amazing?
An inductor is a very interesting device in that when you simply connect a DC power supply across it, it acts as a magnet. It has many applications across all engineering disciplines. Let's take a logical look at the physics behind inductors. A current-carrying conductor produces a magnetic field around it, as shown. Let's do an interesting experiment. Let's bend the wire. As you bend the wire, the magnetic field lines interact with each other and produce an interesting magnetic field pattern, as shown. This magnetic field pattern is similar to that of a permanent magnet, which is why a current-carrying loop acts like a permanent magnet. Clearly, simply by increasing the number of loops, we can increase the magnetic flux. We can also increase this magnetic flux by increasing the current through the coils. A constant called inductance connects between the magnetic flux and the current's value. The value of inductance depends purely on the geometry of the coil. Now, for the most important part of this video, what will happen if the current through the coil changes? When the current changes, the magnetic flux that the coil produces also changes, which means we need to study the effect of this varying magnetic flux on the coil. To study the effect of varying magnetic flux on a coil, we need to introduce Faraday's law. The great scientist Michael Faraday said if the magnetic flux changes across a loop, it will induce an EMF across it. Here you can see that the permanent magnet approaches or leaves the loop. It will induce an EMF across it. This result occurs because the movement of the permanent magnet causes a varying magnetic flux on the loop. Now, let's apply Faraday's law to an inductor connected across an AC power supply. According to Faraday's law, the varying magnetic flux that the AC power source produces will definitely produce an EMF across it. This EMF is known as back EMF, and this phenomenon is called self-induction. The electricity we use everywhere is sinusoidal in nature. It's therefore very important to study the effect of a sinusoidally varying EMF across the inductor. You might have noted that in Faraday's law, everything is about the rate of change. So let's study more about a sine curve's rate of change. Clearly, for the sine curve, the change is zero when the current is at the peak, and the change is maximal when the current is zero. This is one interesting property of a sine curve. The EMF it induces is proportional to the change in current. Therefore, the EMF across the inductor is zero when the current is at maximum. And the EMF is at maximum when the current is zero. In short, the back EMF will vary as shown. If the resistance of this circuit is negligible, the EMF induced across the inductor should be equal to the applied voltage, but opposite in sign. So the applied voltage also has the same variation with the current. When the applied voltage is maximal, the current through a pure inductor circuit will be zero. And when applied voltage is zero, the current flow through the circuit will be maximal. In short, when a sinusoidal voltage is applied across a pure inductive circuit, the current will lag the voltage by 90 degrees. This is a crazy behavior. However, using the fundamental laws of physics, we have explained the reason behind it. We hope you have developed a good conceptual understanding of inductors. Thank you.
After the inductor. In this chapter, we want to calculate the magnitude. Did you see the curve of charging capacitor, something like that, and if charging was something like that? If we are going to find the exact equation and how we can calculate it and other parameters in the capacitor and inductor circuit. Okay, what we are going to learn is factor. At the beginning, we will find a zero input response. Zero input means we are gonna set the all independent sources to zero. That means if we have current source, we are gonna make it current source. How do you set the current source to zero? Open circuit. And for voltage source, yeah. You can see how RC or RN are gonna RC and RM circuit after these three. We then add the first order circuit. Why we call it first order? Up to now, all circuits we had, the equations were algebraic. Yeah. After this, we will see we will have differential equation for RT and RA. Zero state response is when we consider the initial value of capacitors and inductors as zero, and complete response is sum of these two response, zero input and zero state. At the end, we will find, since the capacitors and inductors are linear, we can use this property to find the response to any input which is related to the step of impulse. Yeah. You saw how capacitor is formed and the relationship between voltage and current of capacitor. Charge and voltage of the capacitor is defined by capacity, which is C. Its value, its unit is farad, and the value of capacitance is related to area of the plate A, and the distance between two plates B. If we reduce the capacitance would be higher, and the dielectric permittivity epsilon depends on what kind of material we are using. We can have larger or smaller. As we saw in chapter 2, we can have different kind of capacitor. Here we are dealing with linear time invariant capacitor. Linear time invariant capacitor was kind of capacitor that its relationship between Q and V is a straight line which is going to origin. Yeah? We can easily write Q is equals infinity. V is constant. If we want to calculate I or current, dq over dt, we can I is the constant P ddt over dt. You should memorize the relationship. That's the relationship of LTI capacitor. As you can see here, the voltage across the capacitor cannot jump. But because if you integral from 0 minus to 0 plus, this integral is 0 for every spinning current. Yeah? The only time that this voltage can jump is when current is infinite. Like when we have impulse current. When we have impulse current, this voltage can jump. That is infinite current. Otherwise, you saw in the video that voltage of a capacitor cannot jump. Like unless we have an infinite current, we will see at the end of this chapter one example that we have impulse current. And in a steady state operation, in steady state operation, that means we don't have any varying sources. All sources are constant. So dV over dc, how much in a steady state? Since all the voltage or current sources are constant, these variations should be 0. So we won't have any current. Okay. As you saw in the video, when we connect the capacitor to a voltage source, which is constant, we will see time varying sources after. how much it's gonna be voltage change? It's gonna increase after a while. You will see, you will current and constant. After a while, the current is zero and voltage is exactly the voltage of the capacitor is exactly equal to voltage of the independent source. Here we don't have any current. So you are supposed to memorize these two relationships regarding to capacitor. As you saw, if we have three connection of two capacitors, the equivalent value is smaller or bigger than each of them, since it's smaller. And if we make it as a parallel connection, the equivalent would be larger. We call it inductor as the dual of capacitor. That means if I change V with I, L with B, I with B, I can find this is the relationship of third one. You can find the relationship of inductor from capacitor. Here, if you put I with B, C with L, and again voltage with current, you will reach to this relationship, which is relationship of inductor. In capacitor, we couldn't have jumping in voltage. In inductor, there is no jumping in current. They are two. In a steady state, when there is no change in voltage and current, voltage across the inductor is zero. That means we can replace the inductor with a short circuit. We can replace the capacitor with response. When there is when there is more than 4 time constant of the circuit, you will find the time constant active. In a steady state, as you see, inductor is zero, we can act like we can have different inductors regarding to the coil and their application. This is the relationship between voltage and current of inductor. And as you can see here, IN cannot jump. In a steady state, the value is zero, so voltage across the inductor is zero. That means it's like a short circuit. We can add in inductance when we are connecting the series connection, and for inductors we need to add the inductor. From last chapter, we found we can find Thevenin and the Norton equivalent of any circuit. Okay. That means if I have a resistive network, dependent and independent sources, I can just stop this circuit or replace this circuit because a steady voltage, a very independent voltage with a resistor. We call it as a Thevenin Norton or equivalent Norton. Whatever. Why we are doing that? To simplify. Sometimes this circuit can be really huge, maybe over 12 nodes. And analyzing these circuits are really difficult, so we simplify it as a one small circuit. Okay, RL and RC circuit, they can have three responses. What does the response mean? Finding any voltage or current that they add. Because it responds of the circuit to one input. What are the inputs? Independent sources and initial value. What are the initial values for an inductor? The initial value is initial current. For capacitor, initial value is initial voltage at the time of use. So zero input response means when we don't have any independent sources. The only source of energy is initial condition. What are the initial conditions for capacitor? Initial voltage for inductor, initial current. What is the unit state response? Exact zero state. That means initial state. When we make the initial condition zero, which means if I have R theta again, I should make initial voltage zero. When I have R and theta, I should put initial current. Can I have a circuit with one L and one capacitor like that? Is it first order? Yeah, that would be second. In a first order, we only have one cap or one head. If you have two caps, should be series or parallel. Otherwise, we will have second order. What does it mean, second order? Second, that means the relationship in a circuit is the differential equation, second order differential equation. Complete response is sum of the zero state and zero input. Let's see an RC circuit. For a long time, the key was closed and this one was open. That means we had only these two. This one was open. When we had these two, that means we charged the capacitor to V0. The voltage of this capacitor is V0. At the time of zero, we open this heat and close this one. What will happen if we open this key and close this one? We will have a circuit like that. I have a capacitor, its initial voltage is V0, and I want to calculate how much is the VC or VR over time after T equals to 0. Do we have any independent sources here? We don't have any independent source, which means it is zero input with sun. The output voltage is only related to initial condition. Initial condition we have only in capacitors and inductors. The elements they can take energy. Okay, if I write KCL here, IR plus IT should be equal to 0. And if I write the KVL here, minus 50 plus PR should be 0. That means it should be equal to 0. What's the relationship between IC and DC? Yeah. In a capacitor, the relationship between current and voltage, you should employ IC, okay. If I sub IC here with the relationship, what would be IR regarding to V? IR is current of resistor. Yeah. If the value is R, how much is VC? That means IR is VC. Yeah. How a current can be voltage? Yeah, it should be open. IR is VC over R. Yeah. In fact, IR is VR over R. If VR and V are equal, so I is VC over. If we sub these two in this equation, we will have CdVC over G plus VC over R equals, what's this? First order differential equation regarding the theory. Yeah, that's going to be fine. We need to solve the characteristic equation, which was 3 lambda plus 1 over R plus 2 lambda. Or we can consider as 1. So it's the K e to power of F1. How we can find the K? K is a variable we don't know the way. You have differential equation for K. You didn't. What? You didn't have. You didn't have. Actually. You will have next. You are sending. What you have. We now have the picture. How can you solve this second? For finding K, we should use initial condition. That means if we consider T as 0, we have V0 equal to V here. And K would be equal to B. Here we will find K from initial condition. And at the end, it is the relationship of capacitor voltage with time. We call it tau as time constant or C. And we charge the capacitor to be 0. After 4 time constant, it almost discharges to 0. It takes almost 4. In 1 time constant, almost 37% remaining. We call it as a discharge. How about one RL? RL means we have resistor and inductor. For a long time, EK1 was AB mode and K2 was open. And that means this inductor was charging with this current flow. At T equal to 0, K1 key is going from AB to AC, and we will have only the K2 is closed. Again, we should write the KVL and KVL here if I consider here as 0. I write KVL IR plus IL should be 0, and VL is equal to VR. VL is LDIL over VT. If I write the equation, we will see that again, first order standard equation with initial conditional I0. Again, like capacity, you will see we charge the vector to I0 after 4 time constant. Its current goes to 0. You should know in a capacitor time constant is R3 in inductor is L over R. You should that is easier to memorize because we will show you another way of solving the equation, the first order second without using differential equation. If I change the initial condition to time, to I0, what will happen to the inductor's current? That's the inductor would be 2I. That means 0 input response is the linear response of initial condition. If you multiply initial condition by value, the output current or IN should be multiplied by that value. How much time should pass until we can say if the circuit is settled down? For example, you have a capacitor connected with I have 2 farad capacitors. and 2 ohm resistance. I put 5 volts here and let it go. How much time does it take until this capacitor is charged? We know the voltage of capacitor which are 5 volts, and it's gonna go to when I can I consider this one is almost 0 volt. After 1 second, what do we call the second? 1 second. So we call time constant. After
1 second.
one time constant,
1 over 4.
4 time constant. Yeah, that means it should be 4 time constant. How much is the time constant in our second? Or yeah, 2 farad multiplied by 2 is 4. What's the unit? Second. And 4 seconds. Or say 4 seconds, 4 time constant means 16. That means after 16 seconds, this voltage goes to 0. Now suppose we have only independent sources, but we don't have initial condition. Initial condition is 0, we have only one independent source. This switch was closed for a long time and T equals 0, it's gonna be open. Okay. After that, we don't have this one, we have a P parallel to R, parallel to I. If I consider here ground, I can consider here with P, here with P. If I write it here, I have an I coming inside the node. I should write it positive or negative. Negative. Minus I can write it IP plus IP. How about the current of the resistor? Current of resistor. VP minus 0 over that is VP over. What's the relationship of IC and VP? Current and voltage of the capacitor. IC effect VDV over 6. That means if I move this I to the other side, and write V equal to DV over 6 plus V R plus differential equation. That's a general method to solve first order equation in homogeneous. Which means we have one Q. It looks a bit, however, that's really It's big, you know, but that. Go ahead.
Just-
Okay, if we solve the equation for using this formula, we need to make sure the coefficient derivation should be 1. Okay. Get 3, we should divide all equation by 3 like that. Is it P? Is it P? So I should write e to the power of integral of minus e multiplied by k plus u into the power of e dt. Then you should just replace the p and q in the equation. And I think after that it should be 1. And if you the voltage of capacity over time. Before opening this bridge, the capacitor voltage was how much? 0. Yeah, but both sides is short circuit. After opening that, we are gonna follow the relationship. At t equals to 0, how much is Pt? Ri multiplied by T0, yeah. T to the power of 0, 1 minus 1,
0.
If T goes to infinity, how much is the value of voltage? Yeah. E to the power of minus infinity, 0, 1 minus 0 is 1, which is should go to it's something like. After how long I can say now this capacitor is charged? So, after how long? Four times. After 4. What is now? Hours. And infinity. See that the relation after 4,000 we reach to 98% of the final value. In 1,000 it's almost 53% of final value. That's charge. But that's the thing. You know, if you write this charging, it should be 1 minus 1. After 1. How do you calculate after 1 term? You just need to put T instead of time. Yeah. 1 minus how much is this fee? Or that one sin e power of minus to calculate it, it's 0.633. Up to now, we had only constant independent. So if we have the sinusoidal current or voltage flow, what we have? If that's AC independent flow, what is gonna happen? We usually never calculate RC circuit with AC signals like this. We will find in chapter 7 how we can easily find the answer of this circuit, but just to show you what's the complete response, just we are gonna go through how we calculate one first order circuit with AC independent source. If we put this one at Q and this is P, and we just need to put P and Q in the relationship. That's all mathematics. You should calculate it until you reach this. This is the answer. It looks complicated, but it's not that much complicated because all these are available. These are available. These are available. We have one damping answer and one steady state. These are only the values which are changing with time. Yeah. That means it would be like something like there is a push of E. After that, we will have a sine or cosine function. Then we will connect this as damping answer and this one steady state. We will find in chapter 7 how we can easily find steady state. And we will, when we are in a steady state, Thank you.
Capacitor parallel to that. What is passive component? What is passive? Like they don't generate energy, right? Active components, they move energy on. So the transistor itself. So basically capacitors, inductors, and resistors are passive. So the sources of that. And the capacitor, we don't need voltage source. That's one current source. And why don't you create a current source between? Needs.
Nothing, you just only the way. W what? You can even go out there, the W short key, but the switch. I'm not sure it's.
Yeah. Building SPDT. Okay, so there's a thing symbols to each. SPST, come on. Yeah. That's analog fusion, SPST. Single pole, single throw.
You just right click on it and go to passive components, there's a switch there.
Go to the passive component, there is a switch.
Click on the black
Yeah,
background.
yeah.
We have switch here.
Yeah, smash there. Switch there.
And also.
There. No, you don't need the switch there. You want switch is enough. You put one extra resistor next to your current source as well. Resistor. Yeah. Parallel to that.
No need.
You cannot have a current source open a circuit. The simulator may actually act funky with the current source open. Put a high value. Put a high value.
Like how much?
1000 K.
$70.
Like,
So connect the two. Actually, better than that. Instead of this, why don't you just do it? Why don't you just do a voltage source? Instead? Put a voltage source into it.
doesn't matter.
It matters because
Right.
later the numbers will be off. It will be results that will be wrong. You will create megavolt there that have to come down, etc. Has to
If
be.
we could change the value of
You
the.
can actually take that. Put the voltage source. Simple. Just put the voltage source and one more resistor parallel. Okay. Okay. Put the resistor between here and the switch. So this second, if there was no capacitor, what would be the final voltage? I want a quick answer. What would be the final voltage in this circuit? When the capacitor is fully charged, there is no current going, right? When a capacitor reaches its final voltage, if the current of a capacitor is derivative of the voltage times the capacity, right? So when it reaches the final voltage, there is no current in the capacitor, right? The inductor is the other way around. When it reaches its final steady state, the voltage across the inductor is higher. Right? So a capacitor, when it reaches steady state, is like open circuit. When inductor, when it reaches steady state, it's like short circuit. Okay, so when it reaches the full charge, no current goes in. So all the current goes from here to here and down. So the current through these two are going to be the same. So the voltage of these will be half of this. Each of them will be 2.5 volts. So we expect that at the end it should reach 2.5. Right? At the beginning, if the switch is on, it should be the capacitor empties all the charge into that. So it should be 0. Right? So we want to run it and see how long it takes when you switch it. The switch. So right now, if you actually look at it, is there any current going through the capacitor right now? It's steady, it's charged. So switch it off now.
But you should go and see what
You know, if you check the voltage of the capacitor, so the voltage is quite low right now.
you know, when
It's in the microvolt range, right?
when
So
I could be going earlier.
so how much is the time constant of this? 10 microfarad, 1 kilo. Oh, what is the time constant? You were just seeing the time constant formula that so was teaching, right? Time constant is R times C, right? So how much is the R times C here? Now, people will say why these things are important. If you do not have imagination on these numbers, and when you have this, when you are designing your circuit, you even don't know what values to start to optimize your circuit. So in order to understand on what values you should start, you have to know these numbers. Otherwise, for example, let's say, okay, design a circuit that settles in 4 microseconds. You go and start with some number that say your settlement time is 2 seconds. It's off. Then you sit there and try to optimize it with the simulator. You will be totally confused. You will not be able to do that. Right now, even to be able to see the results of this, you have to be able to calculate the things to start at the right place. If you do not start at the right place, the simulator will show you some fun. How much is the time constant? And how much is the RC? 10 microfarad multiplied by 1 kilo, right? So how much is the RC? 10 milliseconds, right? How many RCs we need to roughly go from 0 to the maximum? Typically, we say 5 RCs, right?
We got it 4 for 19.
4 is okay.
Yeah.
That's
Okay.
so 10 milliseconds. So basically 1 RC is 10 milliseconds. So you want to say, okay, you want to show the circuit behavior. We have to run it for around 10 RC. You see it going to turning on and off, right? So that's 10 times 10 milliseconds becomes like 100 milliseconds. So we need to run the simulation for 100 milliseconds. When you were running the simulation right now, you are running with seconds of what's there, okay, adds milliseconds, right?
Okay.
So actually, so you need to change that scale to zoom your time. So reset it, start from time 0. You have to understand that, and then that's the simulation speed, right? So if you lower the simulation speed, first of all, how do you move the time to 0? It's important that you move the time to reset. Okay, and then simulation speed, let's say, increasing. So that means the time will go faster. Let's try and see what happens. First of all, open the switch. Reset. Open the switch.
I think I have,
How do you open the switch? How do you open the switch?
I have to run it first.
So. Okay. So leave it on. And so 100 milliseconds should be enough for the charge to empty, right? So let's run. See, right now it says the current is 0 here, right? Now, can you plot the current and the voltage? Can you plot this voltage? Scopes. Scopes. Can you figure out where you see the maybe? Options, tools. Go to the tools. Yeah. So, I think it should be scopes. Go to the scopes. That's it. Go to the draw. Let's say. Can someone search quickly, see where you can actually create how to plot the? You have to select the. Where's the plots for plot? We should be able. Oh, it's here. So go to the draw. I just saw the voltmeter. Let's start from the beginning. Let's learn all the. So here there is no sub menu. Let's start from passive components. You see a voltmeter here. So let's go to inputs and sources. Of course, shouldn't be here somewhere, right? Then go to outputs and labels. See, they have ohm meter, they have watt meter, amp meter, right?
Oh, okay.
So add a voltmeter and amp. Okay, here, add voltmeter, so here, voltmeter.
And then what?
Yeah.
Okay.
Put a voltmeter here.
Yeah.
This one should be zero. Connect it the other side. So one side to the one side. Put it vertical. See that, yeah. So you see, one of the things that you also have to become good is in drawing circuits. So you have to see the circuits and see how they are, follow the standards. You basically have to put it vertical. Okay, put it in. Connect this side, this side, this side. Up to here, bottom. Right. Remove them there. Okay. So this one, I'll click on it, see what is the option that it says. Voltmeter. Okay. Series resistance. That's good. It's scale auto. Okay. Okay. Apply. That's the thing. Okay. Fine. Okay. Let's run it again. All right. So this voltage, see, arrive at 0. Right? Now close the switch. goes up around that too. Right? So reduce the speed now, so you can actually see the, then you can come back to plot it. So okay, let's do it again. We said, right, see, first of all, see the voltage is coming up gradually. Right? Why the voltage is coming up? This capacitor is getting charged. While it's still getting charged, there is still current going. Right? But when it reaches 2.5, you will see the current here totally stops. All the current will go from there. But we could do from theory, we could understand that at the end, when it reaches the full voltage, that is because the current is going to be zero. KCL here says the whole current that goes in goes out. So basically it becomes like just two resistors in series connected to a source. Right? So see 2.2, as it reaches the 2.5, it's going to be slower and slower and slower. So what was the time constant that you calculated? 10 milliseconds, right? Now, the actual charging time constant here is not 10 milliseconds. You know why? There's another resistor as well. So what is the time constant of this circuit? So it's actually, from the capacitor's perspective, if you remove that, it's as if two resistors are parallel to each other. So we actually have 5K resistors. So the time constant is 5 seconds, not 10 minutes. So you want to make it 10 milliseconds with this topology. How do you do it? No. Each of them increase it to 2K. If you remove it, when you connect that, that means suddenly this has to jump from 0 to 5. When you are forcing a capacitor at a 0 time constant to go, it's not practical. In real world, that doesn't happen. You cannot have a source with 0 resistance. You want to move a lot of charge rapidly, and then you remove it, then you say, okay, it jumps up quickly, and then basically decays slowly. Right? We will test it. But before we do that, what we want is to be able to show the plots. How can we do the plots? Go to scopes, options, tools, plots, show power, show voltage, show. Go slowly so that you can actually understand where you can actually do the plots. There were examples in the.
You can just put the cursor on it and show.
Okay, can you show? Can you go and do it here? Like this is the tool my son was using for his course, so I'm not familiar with the tool I have seen. But it's free and available. We use Cadence for simulation sims.
Never mind, agents.
You don't know the right path.
For me, but used to show it, but you know, when I hold the cursor on one element, it was used to show the waveform, but
Maybe the double have to save the file.
You have to see what?
We have to save the file.
So save the file. So first of all, add you remove
I'm
this.
not sure about.
So far, Ali has successfully removed the. So now the next step is to add it.
So Sakar was coming to me asking that, oh, these things are, so we already know all of this, I want to go practical and all of this. Fine, but it's pretty much like driving, right? You can talk about saying, in order to drive a car, you open the door, you sit inside, close the door, turn on the car, press the brake, put it in the gear, push the gas pedal and go.
Okay.
But that doesn't make you a driver. You have to practice it up to be able to do all those things quickly. So same with setting up the simulations and things, you have to do that sort of. This is not what we wanted to show them. It's too complex for them. You just want to understand how to copy the plots. How does it do the plot?
Show values.
Show options, show values.
Yeah.
Working with that. Found it? You have the menu up there as well.
Why you? Too many options. Why it doesn't?
I have to go. Browser setting as well.
We need to be probably just on the toolbar, but we need to see the values, so.
You had the plot there, right?
Yeah, only 5 for the first one, that's the only way to show.
But how do you establish it to stay? Good. So now we have a 10 millisecond time constant. Turn off the switch. Then turn on the switch. Please. Reset and start from fresh. Okay, turn off the switch first. Oh, actually, reset. Okay. So now start. First of all, you see, let it deplete. See, it's going down. So we have to speed up the simulation so that it's not to go faster, so that you don't have to wait. Go a little faster as well. Okay, good. Now switch it on. See? Now switch it off. Now switch it on again. Now switch it off. On again. Off. Now keep doing it faster. On, off, on, off, on. Now try to keep it around the line 1 by switching on and off. Bring it down to the 1 and keep it around 1. Don't let it go down. Your purpose, your job is going to be keeping it around 1 with minimum divergence. You're going too high. You're slow. Do it faster. This is what is called a switch mode or switching power supply. Actually, you get the DC-DCs, or you sometimes get AC-DCs.
But anyway, if it's a DC-DC, you have, let's say, for example, you get 5 volts, 4 volts, whatever inside. You say, okay, this 5 volt, I want to control it to be exactly 3. So you connect it to the 5 volt battery. On the other side, you exactly maintain it at 3. Means if it goes below 3, you connect, it comes up. If it goes above 3, you disconnect, it goes down. You keep switching it on and off so that it remains around 3. And you can control it. So these switching power supplies, you can control, say, okay, control it at 2, control it at 3, control it at 1. These phones, they all have switch mode power supplies. Why we bring down the voltage? Because we say, okay, with the chipsets, for example. So the battery of the phone is 4.5 volts, but if you are in the charger, it can become 5.5. The chips that operate there, the best operating voltage for many of the chips is 1.8 volts. Sometimes you want to bring down the power, you bring it down to 1.4 volts. So you need to have a variable power supply on the chip, but you can only have one battery. The battery is 4.5. What you do is exactly like this. This is the battery. This switch, by controlling it, turning it on off. So you put an alley in the phone, whose job is to control it. Let's say, okay, control it at 1.1. I'll control it at 1.5. If you make the simulation slower, you can show better how you can do it. Make the simulation slower. Now your job is to control it around this line that you see here. Don't let it go too much above. Set and start. First, it has to reach them, right? Okay, it's going up. You have to bring down. You went too much up. Up. Up, down. As you see that it's starting to go below the line. Now this is too slow, but it's okay. You can come. Off. Let's arrive at the line. You let it go slightly lower and then you turn it on. Now you turn it on. Off. And so on. So actually, if you become good at that and you are fast enough to detect it, then you minimize the ripple around that. So these things, these time constant things is important. Now, let's say, for example, we remove this. Make it 0. Make it 0, okay. Reset, run. Close it. See, it jumps to the final value immediately. When you close it, it jumps to the final value immediately. It was 0, jumped into the final, right? Now you switch it off. What happens? Shouldn't go 0. And capacitor. Which voltage are you looking at? So that's where the simulator. So why I wanted to show you. The professor was telling us that it's not important. These simulators, if the parameters are getting to the point that it becomes divide by 0 inside, they get confused. They calculate wrong things and you cannot be sure what you see out. So instead of that, you put some small amount. Let's see what we can fix the problem on. The capacitor should be, so this is microvolts right now. This is empty, right? Yeah. This is empty. So now switch it on. So it's 5 volts, right? Now turn it off. The voltage jumped up.
What happens here?
Capacitor was decay.
Huh?
The capacitor was charging.
How did the voltage jump up? And the voltage jump up here? Shouldn't. What it did? Why? Why? Because in order for simulator to be able to converge, you have to put some realistic values. In order to put realistic values for the switch, you actually have inductances there as well. Hidden, you don't see.
That means the model is going to be inductance.
You have your, they model some internal inductance. And therefore, what you, when you suddenly switch it off, it jumps up. It's the same thing. It actually, when you want to run that in the transition, when you go to zero, it actually creates the value. It's going to be very bad off. But let's say, for example, instead of 1 nano, put 1. The jump that you will see, that's right. Right now it's off, right? It's going, it's in the micro, right? So do it again, then, so 5 volts, right? Quickly, fairly quickly. Now, turn it off. Now it doesn't jump. So, see, that's why I am insisting that you have to understand that. If you don't, you will say, oh, so that's the second one, we just do it and it's 0 and it works. Even the simulator cannot converge. Why? Because you have the simulator, the poor simulator has to write the KVL, KCL for the whole network and then go run that differential equation. That differential equation, in order to solve that network of that system of differential equations, you have to have the initial value points for each of your values. All the capacitors and inductances, you have to have the initial voltage and initial currents. And then you have to solve that set of differential equations. It has to apply some intuitive initial values for it. It's not a genius. It sometimes starts from an initial value that is off, right? If the values of the circuit are realistic, doesn't matter what initial value the simulator starts using, because it quickly converges the range that you want. Even if it starts from 10, it quickly comes to the range if this resistance is large, small enough. But when you put 1 nano or 0, 1 nano, or then basically you do not give it any room to dance. You are forcing it to be in that particular position. So the convergence of that solution for the differential equation ends up having problem. It becomes like as if you have an inductor there. And in fact, we will now test with an inductor as well. So we saw with the capacitor, we can bring the voltage up, down from what we started. Put an inductor here as well. So I hope after this session, at least you guys don't say, what is this second theory bullshit? We are wasting our time. No, second theory is the key to electronics. Everything is running around second. Okay. 1 Henry is a very large. So if we want to put some amount of it, how much we will here, I want to put a series inductance here. Here. We are talking about 10 millisecond kind of a time instance, right?
Yeah.
So what is the time constant of an inductor? How much? Wow. Let's simplify this second. Come here and remove this, disconnect the capacitor for now. Keep it somewhere. Yeah, that's good. Let's disconnect. We have 1 nanohenry, right? This is 1 ohm. That's 2 kilo, right? Let's run the simulation, see what happens. We said that. Okay, now the voltage there, it starts going up, but it takes time to go up. Right? Run the simulation a little more slowly so that you can actually.
How much is time constant?
How much is the time constant?
It should be with,
You already taught the doctor. So how much is the time constant?
that is,
Huh?
that is,
Is R over L, right? R over L over R. So how much is the time constant? L over R. 1 Henry over 2K becomes how much? Half a millisecond. So we want to increase it to 5 milliseconds, right? How we do it?
Yeah.
L over R, right? 10 Henry is too much. That 2K go puts
then my
20K. What happened? All right.
Sure.
Reset. Right. It's already at 5 volts.
Slow it down.
The time constant is what? Did I do the right? I increased the resistor. By increasing the resistor, L over R is reduced, right? Yes. So you want to increase the time constant. So you have to reduce the R. It's intuitive actually. You see, inductance resists the change in the current. If you reduce the resistance, that means you want to get more current. That means that inductor will resist that change more because there's more change in the current. If you increase the resistor, you need less current because the change in the current becomes less important. So we have to go the other way around. So instead of 2K, go to 200 ohm. But better than that, let's keep our 2K. And this one, make it 100 million. 100 million. So you have to put 0.1. Right? Now reset and run. So the time constant should become what? It's already at 5, or it was close already. So turn it on, turn it off. Turn the switch off. What happened? 0. 0. Quickly or reset. Let's try. It's running. Let's try. Okay. Turn the switch on. It's coming up very fast. But it doesn't start at 0, huh? Why the plug didn't start at 0? It's coming down. Oh, no, it's down. Now turn off the switch. The voltage has to become 0. Right? Now, switching to 0 doesn't take time because there is nothing that slows down the change. It's only a resistor, right? So it quickly switches to 0. Now, if we add the capacitor, Then switching to 0 is going to take time. So let's do it again. Then reset and run.
Open or close?
Let's start with the open. So we are at almost 0 at the beginning, right? It's micro. And by the way, for simulator, 0 is an approximation. You cannot be absolute 0. So they define thresholds. Say below this is steady. So when you run the simulator to reach the steady state, you define what variation you will accept as steady state. Because otherwise, you need infinite time to arrive at 0. You don't have infinite time to run the simulation. So 0 is approximate. Full voltage is approximate. In engineering, that approximation is important. Now, let's do, so you see this is still remaining around 900 microvolts. 1 millivolt is considered 0 for this. So now turn the switch on. What happened? The voltage starts going up. But somehow the plot is, so run this, make the simulator a little faster simulation speed. Simulation. Yeah, faster. What happened? What's happening here? What do you see?
Alternating.
Make the simulation much faster. Go to the maximum speed. See, finally we arrived at our 5 volts. Now turn off the switch. Takes time to calm down. Right? Now let's do it again. Reset. Start at 0. Okay. You have it here. Run first and then turn down the switch. Keep it fast. Turn on the switch now. What happened? We actually had these large oscillations. Right. And then it started damping and slowing down. Right? So you have those large oscillations. If we stop the simulation, or maybe slow it down a little bit. Let's run again one more time. Reset. Now there is a reason that I can say repeat, because even for me, I have to see how it behaves to understand how I can change the parameters to make the thing work. The purpose of all these courses we do is for you, when you see these circuits, you should be able to intuitively understand what you should change to make it happening the way you want. Because you start saying, okay, I want to build an oscillator at that frequency. Oh no, this is too fast. Now I want to bring it down. How can I do that? So this is what is called settlement time. How long it takes for these oscillations that are this to damp. Why we have the oscillations? Because you have the inductor and the capacitor. The inductor resists the change in the currents. The capacitor resists the change in the voltage. Combination of the two are opposite of each other. So basically it creates a second order differential equation. The second order differential equation creates two poles with real part and imaginary parts. The result of that is an oscillatory behavior with some damping. E to the power of AT is the magnitude. E to the power of j omega t is the imaginary part of it. The combination of it, so e to the power of a complex number is the general behavior plus some DC. you actually see that behavior. That's why using the inductors, you actually can increase the voltage. So let's go back again. Look at here. Turn it off. Okay, start again. So you see here is we have 5 volts. When you switch it on, what is the maximum voltage that you will see? Almost double. Right? So this is exactly what we call how the buck boost DC-DC converters work. If you add those inductors, I think you actually can, with some voltage, you can create a voltage that is bigger than the original. So you actually can use something to create a DC voltage that is bigger than the original. Now this was the AC. We can actually add electronic components to that. If you add diodes, after that you can actually create the voltage. Let's see if we can do it. Let's say, for example, if we add a diode here. After the switch. Okay. Let's start with this. See what happens. This doesn't allow the current to switch back easy, right? So what happens here? Now, he understood that nothing changed. And he realized that nothing changed because you are putting a diode parallel to a wire. Anything parallel to a wire becomes what? Wire. Sure. So let's again. So what happens here? Let's try again. What do you see? It is going down, but it's going down slowly. No, it's not going down. It's connected because it is now connected. Right? The 8.4. Why 8.4? Now, if you now turn off the switch, what will happen? Starts coming down or not? It's going down. He says. That's again. So some of these corners of the thing with ideal devices, particularly for simplistic simulators like this, pushes the simulator out of the convergence region. And if it doesn't converge, your results is bullshit. That's why you need to know the foundation to understand when the simulator is bullshit. Otherwise, you get mistake. There is an old joke that Joha or Mullah Nasruddin was at the was that was basically at the beginning of Ramadan. He decided every day he will throw one stone in the was. So that anytime you can bring down the stone that counts, which day of Ramadan we are in. There was the boy there who wanted to be fun. We went in and threw a bunch of stones in the woods. Mullah had guests. Joha had guests. And then they said, okay, so which day of Ramadan are we in? It's easy, I'll go and check. And then he came back and said, today is 47th day of Ramadan. I said, what are you talking about? Ramadan maximum is 30 days. How can we be on the 47th? They said, what are you talking about? I even discounted half of it for you. So relying on a tool that goes out of range or is corrupted without knowing the knowledge will lead us to the point that we may come back and say, because our simulator is telling us we are on the 47th day of Ramadan.
And you may even apply some wisdom, say, because the simulator said we are actually 96 days. You basically say, okay, it's counting, say 47. It's wrong. So you have to be able to detect what's wrong and what's right. Okay. So we don't know this one. We don't have time to go debug this one now. So remove the diode for now, because that's not the lesson of today anyway. But the lesson of today was the time constants. And let's run it again. So you see, it jumps up to almost double. 5 points. If this 1, oh, if you increase it, what will happen is what? You see, now let's go back to the 2K. So basically, the RC on every side is appearing balanced. Let's change one. Let's reset and start again. You can increase the simulation speed. It goes up, reaches the 5, right? It takes time to load. Now, switch it off. Why it doesn't work? It is coming down, right? Yeah. But it's coming down very slow. So reduce the simulation speed. So why it's not coming down that fast? So we are 10 micro 2K. 2K, 10 microfarad should be okay.
Maybe a little bit.
Huh? Maybe the resistor is not connected. See? That's another thing. So it's not connected. I don't know. You want to play safe, you always put the resistors and then this is not connected. Remove the resistor, or add wire to the 2 sides. Now, put it in the middle. Now add wire. This is one of the things that people suffer a lot in the simulators before they figure out these connections to happen or not. So you have to be able to detect whether your connection is there. Okay, let's run again. We said run. Okay, now let's do it again. Now switch it on. So the 2K here, so remember, if you have an inductor, it actually creates an imaginary inductance. Are we teaching that? Hassan?
Not yet.
Not yet. So
Extra.
effectively, it's like a resistor, but the value is imaginary. But anyway, now the dominant value is the 2K. Now, if we reduce that, make it 100 ohm, we should see the behavior change. Reset and run again. So you see now what happened was it came up, jumped up, and then came down and settled. Right? Switch it off now. Switch off doesn't work.
Register is not connected beginning.
Huh?
That's a register. I think so. Yeah, maybe.
Why wire it to that? Yeah, no, I don't know why are they. Also at the bottom, but when it's red, it's not connected. So it's not connected. You have to connect it to it. Okay, now you're. So let's do it. So these experiments you can do by yourself as well. See, now it's coming down, right? So now switch it on. See, came up and settled, right?
If this inductance is not there, remove the inductance, you remember? Reset and run. It just comes up and gradually settles. When we add that inductor, turn off the simulation first because the poor guy is running in the middle of. Have some compassion for the simulation. Imagine it's your friend. Okay. Turn off that. Reset and keep the switch on first. Off to keep the switch off. Okay. Run it. So we start at 0. Now switch. See, now we have this slight spike. Because this inductance is now small, but starts having effects. Now instead of 1, make it 10. Yeah. See? It is settling roughly around that. Now, why it's settling around that? Because at the end, stop the simulation. So let me, without doing any using any simulation. If we look at that, we say in a steady state, this capacitor will reach the final voltage and it will be open. This inductance will reach the steady state and will have some current, but it will be having a 0 voltage across it. So the voltage here becomes 0, here becomes open, we can remove it from the circuit. So if we want to write KVL, KCL, we have 5 volt, we have 100 ohm, we have 1K. Right? So the voltage, final voltage should be 1K divided by 1.1 times 5. 5 times. This becomes how much? Exactly. We say 1 divided by 1.1 times 5. 4.545. Which is the final thing that you can calculate, right? So these capacitors and inductors in this set, they just create those transient. Now, if this 100, instead of 100, I make it 1K. The final voltage should be what? 2.5. That creates more variation. So now let's see what happens. So that 10 nanohenry brings there, and it's cut out and arrives at the final fairly steady, right? Now, if that 10 nanohenry, we just reduce it and do it, let's say, how much did we have before? 1 Henry, right? Oh, we said 0.1. What will happen? The overshoot will be less. Right? So if you put 1 Henry, so if we want to create Hassan with LC, you want to get like the 10 millisecond kind of a thing. How many Henrys do you need? 10 millisecond. Yeah.
You're thinking it's about who dominance.
Calculated. Okay, put 1 Henry. Put put 1 ohm here. Right? And this one, make it 20K. So what we did here was we made the charging fast. We basically also made the discharging slow. Right? The capacitor discharging, if this resistance is higher, the RC is increasing, it's going to be slow. But the discharging this one is fast. So let's see what happens. Reset that one. See, we started having those oscillatory behaviors that will arrive at the 2.5 amp. By the way, combinations of L's and C's, we use them for creating resonances. These resonances create opportunity to create oscillators, create filters, because you can tune the frequency of them. You want to speed this frequency to this to happen faster, right? What we want is, in order to make it faster, you have to reduce the L and C. So we can reduce the L, for example, say 0.1. Let's run again. Oh, let's run it. Switch it on now. So see, we increase the frequency. Want to increase the frequency further at 10 micro, also make it 1 micro. Do it again. Became much faster. Right? But at the end, it still settles. Why? Because we have those. If this one becomes very high, this one becomes very low, the settlement becomes much longer. So this one's make it 0.1. Or make it 200. Funny. So now switch it off. You're at 2.5. Now connect it again. What happened was I didn't show there. So so that's a 200K, not 200. And these kind of errors in the circuit, when you are designing circuits, happens all the time. You're typing in 200 instead of 200K. Now, if you do not know your theory to go and understand what went wrong, you may spend 3 days in a complex circuit to figure out what the hell went wrong, but it's not behaving properly. So see, the frequency of oscillation is high, but the damping is very slow. It is coming down. This peak maximum voltage keeps coming down, but very, very slowly. Why? Because we do not have those resistors that actually absorb the energy and kill it. So if you have an RLC in parallel, the R that is in parallel absorbs the energy. We have the RLC effectively. But that, if you look at the RLC in that, the damping that we have is very little. Now we want to damp it faster, make it like 2K. Got it. See, the frequency didn't change, but the damping became much faster. So these are the kind of things that you can Now, if you have some electronic circuit, the rectifier thing that would catch this high voltage every time that you switch, and then you can keep switching, and every time you catch, then you can keep increasing it. That's how you can actually generate a voltage higher than what your battery is providing. The DC. That's called buck converter. That kind of converter boosts the voltage. If you want to just reduce it, just capacitor circuits together, that is enough, you can reduce. So you will see all of those in the practical things as well, but I think we can make it attractive by going through this kind of spaces. But please pay attention to those theories, because those are needed. Any question? Sorry, it became a little longer than what we planned, and I think Professor Hassan is a little angry at me, and I stopped the words. But you can review the theory by yourself. Those calculations are supposedly creating the foundation for you to understand what's happening. And use faster. Play with it. To imagine what is happening. In your exam, I may suddenly come and give you a problem to solve on faster. You have to be able to learn. Okay. Any questions?
Is there any possibility to postpone the exam?
I suggested let's do a mini exam on Wednesday. Based on that, we will see where we are. These exams are not for the purpose of rejecting you or giving you say that. The purpose is to basically give you a sense of how much you are and where you are.
Serious.
Everything that we have done. Everything. Not just that, everything until Wednesday. So everything that you get tomorrow, Tuesday,
It's not
Wednesday.
really exam.
Everything that, so learn it on in the class or on the same day so that you can answer the next. In real world, when you are working together, it's not that okay, when we are studying something for the work, it's because we have to apply it now. It's not that we are saying, oh, I'm studying it now, so I can only answer next. I can only answer 2 weeks from. But learning it to be able to apply it immediately. Right? Okay. Any question? My brother. Thank you. Sorry for going off the. But I did not. So Take that part.